talk about some problems of the decision trees. Okay, this is very important. Decision tree is a good model, but it has some problems which you need to overcome to have a better model. So the pros or the positive side of the decision trees is that they do not require scaling or normalization of data. We already have said they are non-parametric. They do not make any assumption about the distribution in the data. Also, they are not really affected by the missing values, to, of course, to some extent. If every value is missing, cannot do anything. So this is a very, many positive sides of the decision tree, but there is a very negative side, which is that they are prone to overfitting. Okay, so what is the meaning of that? That means the decision tree will divide based on some decision criteria until they reach to the deepest level where every leaf node just have one particular sample. That means the decision is particularly fitted for a particular node, and that is something like, let's say, when they're in the class, there are like 40 students. Every student has a different requirement. Everyone is different, their learning style is different, their needs are different. But for that, we do not make one classroom or one particular section for one student. We cannot afford that. What we do, we kind of combine them based on time slots and other thing, and make like 2-3 sections and tell students, okay, if you fit in that section, you take it. So, but decision tree, they will go down and make, for every particular student requirement, they will say, okay, this classroom is your, and only one teacher will teach you for the entire semester. So that becomes overfitting. Okay, overfitting means you go above and beyond, the model prediction abilities, and try to fit the need for every particular data point, which is not good for prediction, because prediction is never for 100% accurate. Predictions can never be 100% accurate. Even the best soothsayer cannot make the best prediction for tomorrow. Okay, so that we need to understand. We'll talk a little more about the variance and stuff lower down here in the graphs, but let's talk about here. So what is the way to stop this overfitting in decision tree? So we said that it grows until each leaf is entirely pure. We have talked about the purity of a node. That is where only one node with 5 positive samples and 3 negative samples, that will be the entirely pure, and it might even go down to 1 sample per node. Okay, so that is based on, there are many features or parameters. So that's overkill. So the solution is to restrict the growth of the tree. Okay, so we want to make sure the tree does not grow so much that it's just 1 sample per node. So we can restrict the growth by a technique called pruning. Okay, pruning is nothing but, you stop splitting a node. So if you stop splitting a node, you put some criteria. Okay, unless it's bigger than this, we will will not split, but if it's deeper than this, we'll start splitting. Okay, so what are the different criterias of stopping the splitting process so that the tree does not grow too deep? So this is like, after a certain depth, we can stop the split. We say that, okay, if the tree is like, let's say 100, height is 100, we will not split it anymore. We'll stop there. So there are many criteria, parameters in the library, which is called max depth. Okay, so when splitting is too uneven, that means one side has 1 node and the other side has 99 nodes, so we'll not split in this case. So it's something like this. There are some parameter, mean samples leaf. We'll talk about it. When too few samples in a node, you don't want to split it anymore. Like if there are 5 samples, you probably don't want to split it again. You probably leave it like that. So it's a mean sample split. What should be the minimum number of samples to decide whether we should split that node or not? And this one, mean samples leaf, was how many samples should be in a leaf. It should not be 1 node per leaf. Okay, that's overkill. So we'll say, okay, let's say 3 to 5 samples, 10 samples, depending on the situation. Okay, you can set those values. When improvement in accuracy is minimal, you keep splitting or making the tree deeper and deeper, but your accuracy is minimal increment. So you say, no, I do not want this. This is time consuming, and it's a lot of cost involved in the decision tree algorithm. So you don't want to do that. Now let's see an example on this mean samples leaf and mean sample split. Let's say the first one, the mean sample split, is 6. That means if you have 6 or more samples in a node, you can split it. and min samples leaf is 3. That means one leaf node should have 3 or more samples. Let's say now this is a node where there are like 5 positive samples and 3 negative samples. So we can split that because this is bigger than this mean sample split, which is 6. We can split that, and then we have, one side 2 nodes and another side 6 nodes. So this is more pure, you can see that, and this is also pure, but this split will not be accepted because the mean samples leaf is equal to 3. Okay, it's less than 3 nodes, so we stop that split. So if we stop some of the splits, then the tree does not grow in that direction, because mean sample split equal to 6. This can also be again divided. Okay, if we stop this particular split, then many other subtrees will not be growing. So those are the different ways. This is just an example that how we can prune a decision tree to make sure it does not grow too deep. Now let's talk a little bit about the bias and the variance. Okay, so bias is the difference between the predictions and the true values. Like you have seen the linear regression where we fit a line through the data points, and we always try to adjust it to make sure that it's the best line. But still, there can be chances that there will be errors between the predicted value and the real value, the true value, the training data which you are seeing, and then those errors accumulate. You have already seen that, and so this, if you have a very simplistic line, you make a very simplistic assumption, oh, that the data distribution is just linear, then you are kind of making a mistake. Okay, so bias is the difference between the average predictions and true values. Okay, so if the high bias means the difference or the error is high, so you can see the error is pretty high here, so we call it a high bias. And also now let's talk about the high variance, exactly what we talked in the decision tree. We are saying we go above and beyond and try to fit a line through every point. Okay, so that is like, okay, in the training data you are good, your line fits, so you get the probably close to 100% accuracy. But whenever there is a test data comes, let's say it's here, and then your model fails to predict that because you have high variance. High variance means how spread out the predictions are. Your predictions are not spread out at all. This is not generalizable. It's particularly fitting to the training data, but it cannot be used for a test data. Let's say I make the video suited for 5 students in my class, and then this 5 students is perfectly, they are very happy. But what about the rest, let's say 40 students? For them, my videos are not good enough. So then we say, okay, my videos have high variance, although it has low bias. Low bias means the error with the training data is less, but whenever we are trying to predict for a new person, new sample, I fail, so my variance is very high. Exactly, that is true for the decision tree. Okay, so we have to somewhere, so this is high bias, means the error is high. It's also high variance because it's a too simplistic assumption. This line, if we make a new prediction for a newly incoming data, and if we extend that line, this is going to fail. Okay, so this is both high bias and high variance, but this is low bias because the error with the training data is low, but high variance because when we predict for a new test data, it fails. So we have to strike kind of a trade-off in between them. We call it the bias variance trade-off. So what do we say that, okay, we have a line, let's say we change, instead of just a straight line, we make it a maybe second degree polynomial or something like that, and we are trying to model the curvature of the data more. So this is like low bias, so the error with the training samples reduces, and also it's generally good in predicting for the new values. So this is both low bias and low variance. We always look for models which have low bias and low variance. And so this is also called one thing, this is called underfitting, okay, because it underfits the training data. It makes very simplistic assumption about the training data and fails to have a good model, good prediction model. So it's underfitting, and this is overly spoon feeding the model, the training data, and this is called overfitting the training data. But this is the perfect model which we'll be looking for. And as I said, the decision tree goes for overfitting. So if we can, it has still low bias, but if we can reduce the variance, if we can make sure that it can, its predictions are more globally acceptable, more generalizable, then we can use decision tree. So that model, a modification of decision tree is called a random forest, and we'll talk about it.